Welcome everyone. It's time to do another LeetCode problem. Today's problem is problem 51, N queens. So the problem says it's an N queen puzzle. So you are given an N into N chessboard where you have to place queens in each row. Okay, and if you're familiar with queens and if you're familiar with chess and how the queen moves in the chessboard, you know that the queens can move in the straight lines, right? Or they can move diagonally in any direction. So they can go this way and then they can go also this way, right? Okay, so uh, the problem says that you are given an n into n chessboard and then you have to put the queens in each row, one queen at each row, in such a way so that the queens can't attack each another. As you can see here, so this is here you can see a 4 into 4 chessboard, you can see here. And then if you look at this queen, you can see that there is no other queen it can attack if it goes in the straight line, or if it goes diagonally, there is no queen to attack, right? Okay, so if you check the other queens here, you also see the same thing. So going in the direction or the diagonal direction, there is no queens to attack, right? Okay, so this is the solution to the problem where you are actually putting one queen in each row where these queens cannot attack each other. Now, the problem here is you are given this value n, you have to create this n into n chessboard, and then you have to place the queens in a way so that they can't attack each other. And there might be multiple solutions. So for example, both of these boards are like 4 into 4 boards, and you can see there are like 2 solutions for that. And we have to find out all kind of solution, like all set of solution. And this is how the output will look like. So basically for the empty space cells, we have to put dot. And so this will look like dot q dot dot. That's exactly what you see here. That's the first row. And the second row is going to be dot 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 q. And that's the second row here, right? So this is the solution for this board, and this part is the solution for this board. So we have to return all of this. Similarly, in the second example, you see the value of n is 1. That means we have just a board of one cell. And if you place a queen, that's the only solution, right? Okay. Now, how do we solve this? Obviously, we'll try to have a board and then we'll place the queens here. What I'm going to do is I'm not going to draw queens. So instead, let's say these are the queens. By the circles, I mean the queens. So I would try to put queen in each row. And then, so for the first row, my algorithm is I want to try a queen in any place in the first row, a valid place. And then depending on where I'm putting the queen, I want to put a second queen here. So you can see I cannot put here, I cannot put here. These are either in straight lines or diagonals, right? I cannot put here, but I can put here, right? So that's a valid place. So I will keep on doing this row after row, right? After I put these two, then I will find another one for this third row. Now you can see I cannot put here, I cannot put here, right? But I also cannot put here, right? But I can put here, right? So I will keep on doing this row by row. But once to find the valid place for the next queen to place, I need to know if that is a valid place. And for that validity, we need to check if there is if the new place is in the same column, right? So, or it's in the same diagonal, or it's in the same negative anti-diagonal, right? So it's in the same diagonal, and then if it's in the same anti-diagonal, because diagonals can be this way or it can be this way, right? So we're calling one of these as diagonals and the other one is anti-diagonal. Now, if you carefully look at this, getting the columns is easy, right? So we can have a hash map and we know that which column we are in. If already we are in a column, so we can keep a hash set for a column set. Say we call this column set. If we put a queen here, we can just put 1 0 in the column set, and next time if I try to put another queen in the same column set, it will first check, and then it will check already this column has been occupied, so I cannot put a queen here. But what about the diagonal ones? What about the diagonal sets? How do we keep track of that? Okay, and what about the negative or anti-diagonal set? So for that, let's carefully notice, let's try to find out how we can do that. So if you see here, we have these columns and the rows and the column values and the rows values. So if you have this, like if you subtract the column from the row, let's see what we find. In the first case, you will find 0 here. Here you will find 0. Here is 0. There is 0, right? Okay, so this one, 1 plus 1 minus 0 is 1. This one, 2 minus 0 is 2. Then 2 minus 1 is 1. Here, 3 minus 0 is 3. 3 minus 1 is 2. 3 minus 2 is 1. So as you can see, basically the diagonals will have the same value. So if I do this, basically the value that it will give me will identify the same diagonal, right? Okay. Similarly, if we look like this, so let's get rid of this. If I add these row values and column values, let's see what we get. So if I add this row value and column value, I get say 3 plus 0, 3 here, and then I get 4 here, I get 5 here, I get 6 here, okay? And then here I get 5, I get 4, I get 3, I get 2 here, right? Here 3, also this one is 3, and this one is 3 plus 1, 4. So you can see that this one now matches the anti-diagonal pattern, right? So this one actually gives me the anti-diagonal, right? Okay, so how do we now do this? So as we said, our plan is to use an algorithm which places the queens in each row and then immediately update all the information so that the next queen, next row knows what are the valid places for the queens. So put, suppose something here, immediately what we want to do is I want to put column 1 as occupied, and then I will put like row minus column. So this is row minus column, row is 0, column is column is 1, so diagonal set will put -1. That means -1 column is occupied, and row plus column, that is the anti-diagonal. So I say 1 is occupied. Okay, next time in the second row, if I try to put something here, let's see what happens. So this one says the column is 2. Okay, column 2 is not occupied yet. That's fine. Column 2 is fine. And then let's do this thing. Let's try to see like row minus column. Row is 1, column is 2, 1 minus 2 is -1. And the diagonal says, hey, row minus column is 1 minus 2 equals to -1. But you already see that -1 is occupied. So this must be in the same diagonal. So I cannot do this because this is already occupied. Okay. Okay. So we keep track of the columns, we keep track of the diagonal values, we keep track of the anti-diagonal values, and every time before I put a new queen there, I keep on checking. So let's do this from the beginning. Okay, so let's start from here. So I start from here, and then for every row, I will try to place the queen in. So this is 0, 1, 2, 3, 0, 1, 2, 3. So this is the rows and this is the columns, right? Okay. So for each row, first I will try to do row 0, right? For row 0, I have 4 options. So I can put the queen in 0th position. I can put it in 1, in 2, and in 3, right? I can put, these are the columns, the column positions where I can put the queen. Okay, so let's put it in position 0. Okay, next. So I have put in the position 0. Next, I move to the next row. And here also I have like 4 options. Okay, so once I put it in 0, immediately I have to update which column and which diagonals have already been occupied, right? Okay, so let's do that. So the column that is occupied is 0th column. Diagonal set that is occupied is row minus column. So it's row minus column, right? And this one is row plus column. So row minus column is row is 0 and column is also 0. So diagonal set is also 0. Anti-diagonal set is row plus column, which is also 0. Okay. Next. Next, we again want to try from 1, 2, 3, 4. First, I will try 0. So I will try this. Now you see that the column already actually collides with this, with the column set. So that means I cannot do this. So this is, now this option is gone, right? So I cannot do this. Next, I try this one, column 1. Column 1 is fine. 1 doesn't collide here. 1 doesn't collide here. That's fine. But the thing is, row is 1 and the column is also 1. So row minus column is 0, right? So 1 minus 1 is 0. And you can see here that this one is, there is already 0 here. That means it collides, right? As you can see the collision here, right? Okay, so this is also ruled out. That means I cannot do this. Next, I tried this. The second column, column is fine. Row minus column is 1 minus 2 minus 1. Minus 1 is fine. And row plus column is 3. So all of these are fine. So that means column is 2. This is minus 1. This is 3. So all 3 are fine. So that means this is a valid position. I am fine with this, right? Okay. So next, let's move to the next. This one now goes to again 0, 1, 2, 3. All options are here. 0 obviously doesn't match. It collides, right? So this is ruled out. 1, as you can see, the diagonal will match. So if you subtract the column value from the row value, or sorry, if you add the column value and row value, that's going to be 3, and you can see 3 is already here. So this is also ruled out. Next, this one column actually matches. If you check here, right? If you check here, these are the sets, so it matches. So I cannot do this. This one, so I cannot do this. This one, you can see the column doesn't match. There is no column 3 here. There is no column 3 here. And then row minus column is minus 1. You see there is a mismatch here. That means there is a mismatch, right? Okay, so I cannot do this. So all these 4 options are exhausted. I'm done. So what do I do now? Next, what I have to do is I have to backtrack. So I was here in row 3, right? I was in row 3. This was row 2. This was row 2, right? So I backtrack. From here, I backtrack to here. So this is what backtracking is. So I just backtrack here. And after I backtrack here, I actually, as you can see, we actually started from 2, right? Okay. So that means this one didn't work. This one didn't work. So what I have to do is I have to delete this. This one didn't work. We couldn't go forward. So let's delete this. So I have to delete all the information regarding this. And then I try a new place. That new place is, you see that this one didn't work, right? So I deleted it. All the information I wanted. Let's try 4. Yeah, why don't we try 4? Okay, so from 4 again we try. Okay, so backtracking and then trying the next one. So then we go to the next row. We go to row 3, and this one is now, it's also starts trying from 1, 0. Let's see. So 0 doesn't work. Obviously, you see. This one works. 1 works, right? 0 doesn't work. 1 works. Okay, so the column is 1. Okay, so before this, when we actually tried 4 worked. So the column was 3, row minus column was -2, and row plus column was 4. All of those are fine. Okay, next, if I try this one in row 3, this one, the column is 1, row minus column is -1, it doesn't collide, and row plus column is 3, that also doesn't collide. So that means this is valid. Obviously this is valid. Okay, so I move to the next one. So I move to the next one. Next one you see is 1, sorry, 0, 1, 2, 3. There are all 4 options. We start from 0, doesn't work. 1 doesn't work. Column 2 doesn't work because the diagonal matches, right? Row minus column is 1. Anti-diagonal actually. Okay, so this one is row minus column is sorry, previous one was 1, just 1. 2, this one, 2 minus 1 was 1. Okay, so this one is also 3 minus 2. So 3 minus 2 is also 1. It's 1. So it doesn't match. So I cannot do this. So you see, I ruled out all 3. Now the next one, this one also doesn't match. Ooh, you see that? This one also doesn't match. This is also ruled out. So what do I do? Well, backtracking. So I backtrack to this previous row. So I backtrack to the previous row. And now I know, say, okay, this one didn't work. Okay, so what do I do? Didn't work. So what do I do? I delete this. I delete all the entries that came with it. I delete all of this. I try the next one. 2. Can I do that? No, I cannot, right? So this one is ruled out. Can I do this? I cannot. Ruled out. Gone. Okay, so next, what do I do? I backtrack again. I backtrack again. Okay, so this time you see that 4, I tell that, yeah, look, 4 didn't work. 4 didn't work. I went down, 4 didn't work. So I delete. So I had backtrack in here, 4 didn't work, and associated with all the values, the diagonal, anti-diagonals, and column, I everything, delete everything. Okay. Then I backtrack to, since this isn't where I backtrack to the beginning. Now I tell this, hey, you see this one didn't work. Okay, so everything failed from that branch. So I delete everything. Now I try again. I try again. The next one. The next one I am trying is 1, right? So I can actually keep on drawing again, you know, the same way, 0, 1, 2, 3. Now let's see. I'm not going to draw anymore. It's going to be the same. So I'm trying this 1, 0, and 2, right? Okay. And then next, from this, I move to the next row. So this is the next row, right? Okay, this is next row. 0 doesn't work. 1 doesn't work. This doesn't work, but this does work. Okay, so 4, 3, this one does work. Okay. Okay, so for that, I put column 3, -2, and 4. Okay, next, I move here for this row. I start from 0. This works. Yes, this works. Okay, so this works fine. I put column 0. I put 2 minus 1, 1, and 2 plus, oh, sorry, 2 minus 0. 2 minus 0 is 2, and 0 plus 2 is 2. Okay, so I put this. Next, I move this here. I can't put here. I can put here. I can put here. You can see that. You can put here. Now, so this one is going to be 2. This is going to be 3 minus 2, 1, and 3 plus 2, 5. Okay, so next I move this here. So now I have I am in the nth row, right? So once I reach the nth row, that means I have completed putting queens in everywhere. That means I have got to a valid state, right? So I will save this state. I will save this state. And I will save this, like saving the answer, right? I will save it in the answer. Okay, so, and now how do I get the other states? Similarly, what I do is I just keep on backtracking. So I backtracked here, right? So I delete this and I try this. This one doesn't work, right? Okay, so that means I have exhausted this. So I will backtrack again, and I will backtrack again, and I will go here. So I will delete this, try this. Okay, that one will eventually fail. So, okay, so if I try this, actually it doesn't work. If I try this, it doesn't work, right? I will also try this. This one also doesn't work. So I backtrack again. This one is exhausted, you see that? Okay, so I will backtrack again, and then I will start from here and then keep on moving, right? Then I will start coming down again. I will start coming down again. Okay, so I will keep on doing this, going forward and back. So backtracking, and then eventually I will get another solution, because this is a 4x4 board, and in the problem description you saw that we have like two solutions. We already have found this one, and then the next one we will get is here, this one. Okay, or did we get the other one? Okay, yeah, so the next one is going to be this one. This is going to lead us to another solution, and that solution is also going to be saved. So this is how we do the algorithm. Now, what is the time complexity of this algorithm? You will get some idea, rough idea about the time complexity of this algorithm. As you can see that for each row, we have n of these rows, right? So for each point, it actually expands, this tree expands to n more. So if there are like n here, in the second row for each of these, like this n into n, right? Okay, then in the third row for each of these n squares, there are n options. So it's n into n that comes from the previous one. That okay, and then there is an initial, for each of them there is also n more options, right? So I keep on doing this until the nth level, right? So it's n into n into n that comes from the previous one, into, for each of them there is n options. Okay, so overall if there are like n levels, n rows, and you see that is n factorial. Obviously for each of them we don't explore everything, right? Sometimes we just stop here. You see, we don't go further down here. But overall, in big O perspective, we can say this is order of n factorial. This is the time complexity. The space complexity, well, at a certain point we just keep this state. That's the maximum, right? At any point I just keep memory of the current state, and that's n into n, that is n square. So the space complexity is going to be order of n square. Okay. So that is the algorithm. I hope you understood it. Now let's go and check the code for this. So here is the code. As you can see, our result is going to be a list, a big list of lists, right? So because there are multiple, each list represents one solution, and each list has n number of strings, because each string is going to represent one row. So each string is going to represent one row. The list of a string is going to represent a solved board, and we can have multiple solved boards, so we need another list of lists. Okay, so there goes the result that we result variable, where we will save all the states of different solved boards. Now this is the solve in queen function. The given only thing that is going to be given is the dimension of the board, and so what we're going to do is we need a hash set to keep track of which columns have been occupied so far, which diagonals have been occupied so far, and which anti-diagonals have been occupied so far. And then we need to save the transitional state of the board. Initially, we are going to fill up the board with all dots, because initially everything is empty. And then we'll keep on filling up different rows with valid queens, and we'll also keep on saving the result in this result list of lists, and finally we'll return it. Okay, so now let's see the main part, how we keep on adding queens to different rows, right? So this is the function, the override and solve and queen function. So we have to know that like which row we are processing. This is the set to keep track of which columns have so far been occupied. This is the diagonal, and the same thing for the diagonals. And this is a hash set to keep track of the anti-diagonals. And this is the current state of the board. So initially we are going to start with row 0, and all these are like empty at the beginning, and the current state is all with dots. Okay. So next, once we go inside, first thing that we have to check is if the row has gone out of bound. That means this is the board, right? So this is the size of the board, the current board. If my row reaches the length of the board, that means the board index starts from 0 up to length -1. So if it reaches this, that means I have filled up the whole, every row in the board, and I'm out of bound. In that case, I have solved the board. So what I have to do is I have to save the current state into a list, right? So the way we do it is we first declare a list, and then we read every row from this current state, right? Every row from the current state, we'll convert every row to one string and add that to the list. Okay, so overall this solved, this is going to be a list of n rows where each row is solved. Okay, and finally we add this solved board to our result, right? So there might be multiple solved boards. Okay, so to the results, we keep on doing this. If my row count goes beyond the size of the board, that means the whole board has been solved. Otherwise, what we do is we are actually in an intermediate phase trying to solve a row. For that, we start, as I explained in the explanation, we start from index 0 and go all the way to the end of the board, right, to the last column. For every column, what we do is we first check if that column has already been occupied, or if the current position that we are trying to do for that particular row and column, current cell, if that current cell is in a diagonal position with another cell that has already been occupied, or if the current cell, the row column cell, is somewhere which is already been occupied in an anti-diagonal set that is already been occupied. If none of these are true, that means that's a valid position. This row column cell position is a valid position. So first thing that we have to do is I have to set that cell to Q. That's a valid position. And then I have to add the information about that cell to all these three sets. Okay, I have to add the information, and then I move on to the next row. So I increase the row by 1 and send all the current state, right? So I have changed the states here and pass everything in recursively for the next row. Once I'm done with this, I have to backtrack, right? So this is the backtrack portion. For the backtrack portion, I have to bring whatever I had changed back to the initial position, right? I explained in the drawing explanation. So what I have to do is I have to set this again to dot character, and then remove all the cell information that I had put from the column set, diagonal set, and anti-diagonal set. Okay, so I keep on doing this, and so this way I try each column, and for this particular row, then this thing is solved. And recursively, I'm calling one after another. So recursively, I'm calling the next row until I reach the final row and go beyond, and then I copy the result. Okay, so if I keep on doing this, ultimately this result variable is going to have all the solved boards in it, and finally I return the result. That is the list of all solved boards. So that's it. Thank you very much for watching. We'll come back next time with another problem.